This video will be recorded and then I will upload in my what you call the YouTube channels. Okay, so I will create a playlist for this master's video notes so that you can refer. Okay, so this is for to tackle for students who are unable to attend the class due to several constraints such as internet stability and so on. Okay, so so DC power and AC power is quite different. Okay, for the DC power, as you may recall, we have only one kind of power, which is we call uh, active power, or sometimes P, which is you measured using watt. Okay, but in AC power, we have three different kind, which is P, which is active power, and Q, this one is reactive power, and S, which is this what we call apparent power. Okay, so no need to worry because we will go each power of definition of all this power in our slide today. Okay, so as you can see here, we have DC and AC power. Okay, so we have, because we have a DC circuit and we have also AC circuits. So they are what you call during at the earlier years in around se- 70s and so on. So there are some what you call argument between the people that actually prefer or favor to the DC power, and there are also a group of people that are favor for AC power. So these two group of peoples arguing to each other, and but somehow, so actually for the DC group, the leader is Thomas Alva Edison, and for the AC group, okay, are led by Nikola Tesla, okay, who invent the induction motor. Okay, so these two people argued each other in scientific argument, and but somehow the AC group win. So starting from that, all our power system delivery, our power system generation, and so on are actually use AC power form. Okay, because of what? Because there are several limitations of the DC power. Okay, so as you can see, we have two types of DC and AC. So this is the first figure shows if we use DC system to generate and transmit to the load. Okay, so the generator, as you can see, need to generate 480 volt DC, 100 ampere, because your load requires 100 amperes. Okay, so to transmit this, so you need to transmit 100 amperes. Okay, so it's quite the current is quite big. Okay, and then so meaning that if your current is high, so there will be big losses during the transmission. Okay, but for AC system, there are advantage. Okay, so as you can see, the load requires 100 amperes. So our generator will actually generate the same amount of current and also voltage. Okay, but to transmit, okay, from the generator to the load, it use what we call a transformer. So this transformer will step up the voltage and at the same time will step down the current. From 100 ampere, it only transmit 10 amperes only. Okay, by boosting up the voltage. Okay, and then after at the end of the receiving end here, it will step down the voltage again to 400 to the original 480 volt, and the current will actually increase back to the original 100 amperes. So this is actually the advantages of AC system. Okay, because the AC system, during the transmission, the losses is very, very low. because the current right now is very small. Because we know the power losses is actually V multiplied with I, right? But we can also write this equation in terms of I square R. So if your current is high, because this is is actually R losses for the cables. Okay, so if the current is very, very high, so as you can see, the power losses is also very high. So that is the relationship between losses and also the current. Okay, so that is the advantage of using the AC system because of the losses, low losses during the transmission um, line. And at the same time also, for to transmit the AC power, the cables used is actually what we call a very low grade cables can be used. Okay, so meaning that the cost to develop or to construct the cable and so on is very cheap compared to the DC power transmission. If you want to transmit the DC power, okay, you need to have what is called a solid cable. Meaning that from a copper, you need to have a solid copper as their transmission line. Otherwise, if you use several copper cable and then laminate them together, group them together, so it will create a lot of losses. For example, eddy current loss and so on. Okay, so that's why to transmit the DC power, you need to have a solid copper. When you have a solid copper, the manufacturing cost is very, very high compared to cable that for the AC current. Okay, so there are two disadvantages if you are using DC power for the transmission. The first one is actually high losses, and the second one is due to the cable cost. Okay, the manufacturing of the cable is very, very high. Okay, so this is the AC waveform. Okay, so please bear in mind that for AC system, our voltage and current must always in sinusoidal form. Okay, so for example, we have the voltage and we have the current. And if the voltage and current, for example, for this phase, we have the voltage, the blue color one, and then the purple one is the current. So if you can see, this has no different in terms of the angle. So this one we call in the voltage and current are in phase. But if you have a voltage and current that are lagging, for example, this current is like this and the voltage is, so we have a phase difference. Okay, so this one we call a phase delay between the voltage and the current. This one will introduce what we call the power factors. Okay, so we will also look at what is the power factor, because this power factor will actually affect your electrical bills. Okay, if you have high power factors, you will reduce the bills. But if you have low power factor, your electricity bills will also increase. This is related to P, Q, and also S. So this is the AC power. So they are more complicated compared to when you analyze the DC circuit. Okay. So so in this present world, okay, so right now there's a problem with our power system. The problem is our generator is generate AC power, and our transmission line also is actually transmitting the voltage and current in AC form. But our home right now, the load that we use in our home is majority of them are DC load. For example, our LED lamp, our house lamp right now, So before this, we are using bulb, right? Tungsten bulb. You use a fluorescent bulb and so on. So that one is AC, and that one is not a very efficient. So right now, our home, we want an efficient lighting and so on. So we convert into a DC load. So most of our home right now are DC load. Okay. The example is our LED lamp, our laptop charger. Okay, what else? Actually, our TV, our television is actually working on DC voltage and DC current, actually, because we are using semiconductor, we are using transistors. Okay, our computers also are actually using DC power. So our socket outlet right now, our home is actually producing AC power. So we need to convert that. Okay, so for our computer to turn on and our television to turn on, so that need a conversion from AC power from our socket into a DC power. So that conversion, okay, requires another electronics equipment that built in inside your computer and television just for the power conversions. So that power conversion create losses and so on. Okay, so that is the dilemma in our power system right now. So our power system is AC, but our load is DC. So and then we need the conversion circuit and so on. So they create a lot of what call problems in terms of high losses, energy wastage, and so on. Okay, so maybe you ask me, maybe you want to ask me, why don't we just use DC to generate? Why don't we generate DC power? Right? Because our load is DC, so it is very wise if we produce for generator producing a DC power, right? But you need to bear in mind that we have the problem on the transmission side. The transmission, okay? So it's good because our load is actually DC. So it is good if we can actually just use a DC generator, right? And then transmit. But the problem is actually on the transmission problem because losses, okay? And losses problem, and then the second one is what called the cost, the cable cost. So that's why we didn't use DC generator. We use AC generator. Okay, but we have load here, DC load. So we don't have much choice. We need to do some AC to DC conversion. Okay, we need extra conversion. For example, our laptop, we charge the battery, right? We charge the battery. The battery require DC voltage and DC current. So we need to have charger. So your charger is actually your AC to DC converter. Your charger is your AC to DC. So that is actually equipment that actually built also inside your computer, your CPU power supply, and your television power supply. So they are built in with this AC to DC converter circuits. So this conversion has a lot of what you call losses and so on. Okay, so that's why we don't have a DC generator because of these two major problem, the cost and also the losses. But there are research and there are also a motion to have what we call, so right now, this one we call, this type of generation, we call centralized. Okay, centralized meaning that we have the generator, which is very, very far from your home, and then we transmit to your cities. Okay, so this generator is very, very far. So you need to have a transmission line very far away and so on, and then go to your cities. Okay, so this is what we call, this is the way we actually our power system. So this one we call the centralized generation. So all the generator is centralized here and then transmit the power to the cities. Okay, there are also right now a motion where we as our home, okay, we produce our own electricity. So that's why we install a solar panel. We maybe have a wind turbine, okay, and then we may have our battery storage at the back of our home yard and so on. So this one will actually supply our home, okay. And if the power generation is beyond of our usage, so we can actually sell to the utility. So this is the motion right now, and we can see that our TNB, okay, under what we call SEDA, SEDA, this is our government agency. They encourage the installation of the solar panels and so on. Okay, this is what we call right now the generation. Right now, the generation is somehow much nearer to the load. So this is what we call distributed generation scheme. Okay, so every house is a generator. We generate power for our home, and if the power generate is higher, then we can sell to the TNB. Okay, so it's much good because the solar is actually DC power, because the solar panel is actually supply DC power. The wind turbine also a DC power. So there is no needs for any circuit conversion. So you can use it directly. Okay. So that is the advantage of this distribution generation, because we want to what we call, no need to have another transmission tower or transmission line and so on. So we distribute. Every house is a power generator. Okay, how we can sell? I cannot sometimes, sorry, because the chat here. Okay, we can sell extra power. Yes, yes, we can sell extra power to the TNB using what we call this what we call net metering. Net metering. So actually inside the house we have a meter, right? This meter that there is 2 meters. The first meter number 1, meter number 2. Meter number 1 is actually the meter that measure all your power usage, and the second meter is actually the meter that monitor the power that you sell to the TNB. Okay, so meaning that you have income from your generation of your solar panel and so on. So right now they actually there are a lot of renewable energy. We call this renewable energy. We have solar, wind turbine, and so on. But right now, SEDA, the agency, this is not a private sector. This is our government agency that monitor the installation of the renewable energies in Malaysia. Okay, so right now, SEDA only approve the installation of solar panels only. Okay, the wind turbine, they still didn't approve yet. Okay, because actually in Malaysia, wind turbine is not very appropriate because the wind velocity is lower than the standard velocity to generate electricity. Okay, because to generate electricity, you need the wind to be larger than 3 meter per second, the speed. But based on the study in Malaysia, usually our wind speed is lower than this velocity. So it is not suitable. For Malaysia, it's not very suitable. But for the countries that, for example, Denmark, German, okay, Sweden, and so on, their wind velocity is very high. Okay, very high. So that's why they are generating their electricity using wind turbine. And just for your information, uh, in year 2020, the German, okay, Denmark or German, I think, they have successfully um, implemented their objective where 100% of their energy supplies is actually come from the wind turbine. 100%. Malaysia is very, very far away. We still depending on the coal, okay, on the coal generator, batu arang tu, and also hydroelectricity. But hydroelectricity is also not very high compared to other countries. Okay, so for the hydroelectric, is actually an AC, is generate AC because you know, when you have the dam, so the water will actually go down from the kinetic energy, so it will actually rotate. Okay, this is a turbine. Okay, so it will rotate this turbine, so it will generate AC electricity because the turbine is actually like a motor, like a what you call electrical motor, right? So it will generate because it will rotate. So the rotation will create a AC voltage and AC current. So hydroelectricity is essentially an AC form power generator. Mostly the DC power generator is actually come from the renewable energies such as our solar, the wind turbine, and so on. Okay, even though this wind turbine is rotating, but actually inside that is actually uh, they have some circuit that actually produce DC power. Okay, can we move? Because when I'm okay, okay, this is actually not our main part. Actually, this is just for review of what is actually the difference between DC and AC, and then what is the problem. So actually, one of my friend, he did a PhD in transforming the DC system. So because right now we have the load is actually DC. Most of our load is DC. So why not we have a DC system inside their home? Okay. So he tried to reconstruct the wiring inside his lab in UK, inside his lab, but it's quite difficult because a lot of new materials, cables, and so on. So he didn't manage to get that conversion. Okay, so it's quite difficult. He said it's quite difficult because a lot of things need to be done at the higher level. But it's possible. Okay, it's possible. Okay, so right now, just I want to have your input on this. Can you calculate for me for this circuit? What is the power for this circuit? You have a DC voltage here, and then connected in series with 10 ohms, and also connected with an inductor. Can you calculate what is the power of this circuit? Okay, just give your answer in the chat room. You can also privately chat with me to give the answer if you are very shy. Okay, so 0.4 watt. Okay, so the answer is correct, 0.4 watt. Why? Because uh, you need to convert, okay, this 1 millihenry, you need to convert into what you call the reactance. You cannot solve this circuit using different units. This is ohm, this is millihenry. So you need to actually convert 1 millihenry into reactance. Reactance have a value of ohm, okay? Because we know X, the reactance of the inductor, is 2 pi FL, the unit is ohm. So right now, your inductor is 1 millihenry. But what is the frequency of this circuit? Yeah, the frequency of this circuit is 0, right? Because this is DC voltage. So your frequency is 0. So meaning that this one all becomes 0. So this is 0. So meaning that it is short circuit. So that's why in DC circuit, the inductor is short circuited. Okay, so meaning that the only element that actually operated in this circuit is only this element. Okay, so from that, you can calculate your I V over R. So 2 over 10 ohm. So you will get 0.2 ampere. And then by using calculation I square R, so you just 0.2 square multiply with 10. So you should get 0.4 watt. Okay. So please bear in mind for DC circuit, your inductor will be always short circuit, and for the capacitor, when it is involved with the DC circuit, your capacitor actually will be open circuit. Okay. So I hope you can get this one. Okay. So for the DC circuit, we have only one power, which is P. Okay. And the unit is watt. Okay. So I think we can go deeper on the AC power. So after completing this lesson, after this, you should be able to differentiate the instantaneous power, which is PT. Instantaneous meaning that it depends on time. Okay, depends on time, time dependent, and the average power. This one is P, or sometimes we call also active power in AC circuits, and understand another type of AC power available in R, L, and also C elements. Okay, here we can have P, Q, and also S. Okay, due to this element R, L, and C. Okay, because in AC circuit, the value of inductor and capacitor has significant impact on your P, Q, and also S. Unlike the DC circuit, where for the DC, L and C have no impact. L is short circuited, while C is actually open circuit. So that's why we have only real power, P. But when in AC, because with AC we have frequency, right? We have frequency, so that's why we have XL and we have XC. Okay, so the power calculation, we can move to the power calculations for the AC power. So you need to mind this one, passive sign convention, okay? The passive sign convention said that the power is positive when the current is entering the positive terminal of the element. Okay, so that you get positive sign. Okay, make sure that if you want to have positive sign, the current must entering the positive terminal. So that is what the passive sign convention. So when you have positive, meaning that this element is actually absorbing the power. Okay. So for the AC circuit, so we know that the AC, the voltage is instantaneous, change with time due to also the current. So we have VT and IT. So the power absorbed by the element, we can calculate this one. PT is the instantaneous power, okay? Instantaneous power is equals to VT multiply with IT. So that is the instantaneous power. And we know that if the voltage is a sinusoidal in the cos function, and the current is also sinusoidal, so to get the instantaneous power, so you need to multiply Vt and It. Okay, so like this equation. And if we use the current as our reference, so we can write down this equation like this. So we move all the angle to the voltage because we use current as our reference. Okay, so right now the voltage will become Vm cos omega t plus theta V minus theta I multiply with Im cos omega t because we use current as our reference. Okay, and then by using the trigonometric identity, we know that cos A cos B is equal to this one. Okay, so we rewrite that equation of our instantaneous power like this. So we have uh, this one, and then we have the second one. So right now, as you can see, this is actually a constant right now. This is a constant because we don't have omega t here. But right now, but for the second term, we have omega t. So we want to what we call expand this. Okay, we want to expand this further. So we use a trigonometric identity also. We know that cos alpha plus b is equal to cos alpha cos b minus sin alpha sin b. Okay. So mean that this one is your alpha and this one is your beta. So cos alpha plus b plus beta. So we expand this one. So finally, this one is the first term, the original first term. Okay, the original first term. This one is the second term that we have expand. Okay. So the first term and then the second term that we have expand. This one. So right now, as you can see, we have a constant here. Okay. We have this one constant. And then we have also a constant value here, cos alpha, cos theta v minus theta I. And we have also another constant here. So from here, Vm Im over 2 cos theta v minus theta I, we define as a P, which is our real power, while Vm Im 2 over 2 sine theta v minus theta I, we define as Q. Okay, where P is actually active power. Active power, okay? So this one is actually time independent. As you can see, there is no omega t here. So it is constant. And then Q is what we call the reactive power. So we have active power and reactive power. So the unit is actually watt, while for the Q, the unit is var. VAR. Okay, VAR. VAR. Okay. So right now we have introduced you instantaneous power, and then active power and reactive power. So this equation of instantaneous power can be reduced, or we can write down as these equations. The instantaneous power is equals to active power plus active power cos 2 omega t minus reactive power, which is Q, sine 2 omega t. Okay? So what is P? P is this one, which is I have already explained. And Q is reactive power measured in VAR. Okay, so this is the most important part, I think, for this for today lecture. Okay, the instantaneous power. Sorry. And then reactive power, and then active power and reactive power. Okay, so sometimes P also we call real. It has a lot of names: average, real, active. Okay, actually, these three names actually referring to the same parameters, which is P, while Q is actually got only one name, reactive power. Okay, and then okay, so we move towards this one. Okay, so meaning that in AC circuit, okay, we have, as I told you earlier, we have three types of power. Okay, the first one that we have already defined is actually real power, which is in watt. And then we have what we call reactive power. So this one is P and this one is Q. And the overall of this one is what we call apparent power. The unit is VA. Okay, just VA. The unit for power is watt. The unit of reactive power is VAR. And the unit of apparent power is VA. So meaning that inside AC power circuit, we have three types of power: P, Q, and also apparent power, which is S. Okay? So from here, the instantaneous power, we have already know the equations. So this PT is equal to P plus cos 2 omega t minus Q sine omega t can be plotted as follows. Okay? So this is your voltage and the current. And this one is actually the plot of your instantaneous power. Okay, I just want to let you know that this class will not be fully 2 hours, okay? Because we know that the student cannot focus for long time of lectures to 2 hours. So I will just limit the class for maybe only 1 hour. Okay, and then after that, maybe you can have extra, what you call, exercise by your own. Okay, so just to remind you that the nature of our teaching and learning right now in university is not lecture centric. It's like more towards on the student centric. Okay, the student find the problems. The students, what I call, all actually self-dependent, but the lecturer will just be a guidance or maybe a facilitator. Okay, that is the way right now. Okay, so we move back to this slide. Okay, so this is the plot of your instantaneous power. So you can see we have this one is the zero. This one is zero, so meaning that this one positive and this one negative. Below then this one is actually What should? It's actually negative. So meaning that you have positive and then you have negative. So you have sometimes you have the value of positive value, positive, and then at this point you will have your value is actually negative. Okay, so meaning that what is the positive? Meaning that positive and negative. You have sometimes the instantaneous power is positive, and sometimes the power is negative. So what is mean? Based on passive sign convention. Positive. What is mean by positive and negative? You have right now positive and negative. Sometimes it's positive, sometimes the power is negative. This means that in AC circuit, sometimes the load is actually consume the power, absorb. But there are also some time where the load is actually generating the power back to the circuit. Okay, you can see here. This one is a positive. At some point, this one is a negative. So meaning negative, meaning that when your power is negative, meaning that you supply to the circuit. Okay, so that is the complexity of the AC circuits, because you don't know why is sometimes supply and sometimes it's actually absorbing. Okay. Okay. So right now, let's see in deep when you have three types of load. We want to see the power involved. Okay, the power calculation involved when you have a resistor, when you have your load as an inductor, and when you have the capacitor. Okay, so I want to take a break about 5 minutes. Okay, 5 minutes. Take a break 5 minutes. Okay. So let's resume on this slide. Okay. So this is let's say we have a circuit AC that connected in series with a pure resistive load. So right now in phasor, so we have, for example, I give you 10 volt with an angle of 0. And this resistor is 10 ohm. Okay, so right now we want to analyze what is the power that involved when you have a pure resistive load. So what you need to do is to get the current and to get the voltage and the angle between the voltage and also the current. Okay, you want to get the voltage, the angle of the voltage, the current, and also the angle of the current. So right now, the angle of the voltage is because the load here, okay? So since this is connected in series, so meaning that the voltage here is actually same with the supply load, okay? Same with the supply, so 10 volt, okay? So this is referring to the voltage across the resistor, okay? Because you want to see what is the power on this resistor, okay? So the voltage across the resistor is similar to the supply, which is 10 volt. The angle of the voltage is also is actually 0. And then the current is actually V. The current is just V over R. Your V is 10 volt, angle 0. The resistor is 10 ohm. There is no angle. So your current is 1 ampere with an angle of 0, right? Okay. So by using this calculation, Vm equation, Vm Im over 2 cos theta V minus theta I. So you will get some answer, right? What about Q? The reactive power. So Vm Im over 2 sine theta V minus theta I. So right now your theta V minus theta I is 0. So sine 0 angle is 0, right? So that's why for a load, for a system, AC system that connected to a purely resistive load, you will not have Q. Your Q is 0. Okay? So you have only active power, which is these values, because cos theta V minus theta V minus theta I is 0. So cos 0 is 1. So that's why you have Vmim over 2. While Q is 0. So your instantaneous power equations becomes P plus P cos 2 omega t. And if you want to plot, so this is the plot. Okay. So you will see that all your power is actually a positive power. There is no negative like this. Okay. You have sometimes positive and then you have sometimes negative. But when you have your resistive, your load is a resistive load, you will see that your instantaneous power is always positive, always greater than 0. Okay, this is your 0. 0 plane here. It's always greater than 0. Okay, and this line here, this value is actually your active power, P. Your active power, Vmim over 2. So this is the value, this height. This is your constant value, okay, which is active power. Okay, let's say on purely inductive circuit. So purely inductive circuit means that your load is connected to a inductor. Okay. So you have, for example, 10 volt 0. Okay. And then my my reactance is J 10 ohm, positive J. Okay. Positive J 10 ohm. Or in my phasor is 10 with an angle of 90 degrees. Right? Correct? Is it correct? Like this. So since this is connected in series with the supply, so this one is also your voltage supply also. So meaning that your voltage of the inductor is 10 volts. Your angle of the voltage is actually 0. And the current of the load here, IL, is actually IL. So you need to calculate. Your IL is V over X. Okay. So your V is 10 and your X is 10 90 degrees. So you become 1 negative 90 degrees. So your current is 1 ampere. Angle of the current is negative 90 degrees. So what is the power? P. So Vm Im 2 cos your theta V minus theta I. So 0 minus 90 degrees. While for Q is Vm Im over 2 sine 0 degrees minus 90 degrees, right? So cos positive 90 degrees, cos 90. So it's 0. So this one becomes 0. So your power is 0. But your Q, so since sine positive 90 degrees, so this one become 1. So your Q is positive Vmim over 2. So from here, what we can conclude that if your load is a purely inductive, okay, only consisted of inductor, there will be no active power. The only power that exists is reactive power, which is the value is Vmim over 2, and your instantaneous power. So this one is your instantaneous power, the equation P plus P cos 2 omega t plus Q cos 2 omega sin. So this one will become 0. This one is also 0. So you will have only this one. Okay. So this is the plot of your instantaneous power, PT. So right now, as you can see, you have negative and also you have positive. So you have negative and then you have positive power, which is the area under this graph is actually from this negative and positive is actually similar. So if you average them, so you will have your P average is 0, which is translate to why your average power is 0, right? Because P is actually, they got a lot of name. So active, average, and then what else? Real. Okay. So when you average this waveform, you have negative and positive, which is have a same area. So your average value is 0. So that translate why you don't have active or average power. The only consist is actually reactive power. And your instantaneous power waveform is like this. And as you can see, this voltage and current across the load is, as you can see, is this one voltage. Okay, this one voltage and this one is current. As you can see, the phase difference is 90 degrees. Okay, so if you have your voltage and current has a phase delay 90 degrees, so you know that your load is inductive load. Okay, purely inductive load. Okay, the last one is the capacitive load, and I think this one I don't want to have. Okay, sorry. Okay, just before we proceed with the capacitor, just want to let you know that you have the phase delay right here, 90 degrees, and you can see that the current is actually uh, following the voltage. You have the voltage first, and then after that, then you meet current. Okay, so we say that for the inductive load, so the current lag voltage, lagging voltage. Okay, the current is lagging the voltage. So if you see that the current is lagging the voltage with an angle of 90 degrees, so you can sure that you can confirm that your load is actually purely inductor. Because sometimes people say, okay, based on, because for example in the outside real world, okay, you don't know what is type of load here, so you just look at the voltage and current waveform. So if you see that the current is lagging the voltage by 90 degrees, then you can just tell them no need to see the circuit, we know that the load is actually inductive load by only looking at the waveform. So that is how the engineers actually analyze, okay, by seeing the interrelationship between the circuits, the waveform, and so on. Okay. So this is the most important part. For the inductor load, the current will always lagging the voltage by 90 degrees. And the power is 0. Real power is 0, but the Q, we have some values. The same with the capacitors. Okay. The same with the capacitors where you have also your P, real power is 0. Okay. Okay. Your real power is 0, but your Q right now is actually negative. Okay, your Q is negative. So if your Q is negative, meaning that your load is actually a purely capacitive. Okay, and the current must lead the voltage. So if you see the current lead the voltage by 90 degrees, you can confirm that the load is actually a capacitor. So how you can see? So this is the voltage and this is the current. So you see the voltage, for example, this one. Okay, the current is actually leading. Okay, the current is actually leading the voltage by 90 degrees. So if you see that the current is leading by the current is leading, so it is a capacitive load, purely capacitive load, meaning that your P is 0, your Q is negative. Your inductor, if your load is inductor, so your Q is positive. And this is your instantaneous power, okay? And for the capacitor, your Q is negative. And this is the equation for your instantaneous power. So for instantaneous power, as you can see here, this is your PT. The area up and also down here is equals. So if you average for one period, so you will have your power average is 0. So that's why you have 0 watt here. Okay. So this is the important part here. For the capacitor load, the current is always leading the voltage by 90 degrees. Okay, so to summarize the lesson from the previous slide. So if you have a resistor, purely resistor, so you have a positive active power but 0 Q. If you have inductors, so your active power is 0, your reactive power is positive values. But if your load is a capacitor, your reactive power is negative value. So you need to memorize this one because this one will be what they call the fundamental elements to proceed with our power calculations, power factors calculations, and also our three-phase power calculation after this. So any questions? Okay, so if there is no question, then I think we proceed a little bit. So this is actually the power meter that shows the AC power. So usually this one is installed for AC power system. So it will give you all the informations required. You have the what you call the average power, which is in kilowatt. It will give you the reading of your Q, okay? And then it will give you the reading of your apparent power, the frequency of your circuits, and so on. Okay, so if you have both kilowatt and you have both kVAR, meaning that you have positive and your kVAR is also positive, what is mean your load? What type of load? What type of load do you think? If you have both, you have P, positive P, and you have positive Q. Huh? Inductive, yes. Inductive, meaning that you have resistor and inductor. Yes, R and also L, because R will provide P values while L will provide positive Q value. Okay, if your Q is negative, okay, if your Q reading is negative, give you a reading negative, meaning that your load is R and C. Okay, so this one we call not purely inductive or purely resistor. This one we call inductive load. And this one we call capacitive load. Okay, so there's a difference. Okay, purely inductive, purely capacitive. Purely inductive meaning that you have only a single inductor. Okay, but if you have combination of R and L, so we call this load inductive load. And for capacitive, you have R and C. So if you have inductive load, meaning that your current is lagging the voltage. Okay. For the capacitive load, the current is leading the voltage. Always, please memorize this one, because as an electrical engineer, you need to know this relationship. Okay. So if the current is lagging the voltage, so you know that your load is inductive load. If the current is leading the voltage, so you know that load is a capacitive load. Okay. So right now, can I ask you what type of? So right now we have three types of load right now. Resistor, which is I think not possible in real world. So we have two types of load right now: inductive load and capacitive load. So I ask you, what type of load our house that the grid see? Dia nampak rumah kita ni jenis what type of load? Is it inductive load or capacitive load? When we want to do a mathematical analysis, we always model. For example, we model the electrical bulb. What is the bulb? For example, the fan, the blender, the washing machine. What type of washing machine is it? Is it capacitive or is it inductive? For our ceiling fan, is it a capacitive load or is it an inductive load? Our blender, our lamp, lighting, is it capacitive or is it inductive? So the total of our load inside our home will determine what type of load our house is. Oh, capacitive. So Muhammad Safwan, capacitive. Okay, capacitive. So any other answer? Why you say capacitive? So actually, capacitive is quite difficult to it's quite difficult actually. Our house, our load, for example, the fan, the washing machine. Okay, what else? For example, the fan and washing machine. It's actually inductive load. Why inductive load? Because you use a motor. It use electrical motor, and electrical motor is actually inside that we have a electrical winding, a solenoid, right? Because the basic principle, the basic construction of the inductor is a solenoid. So a solenoid, and then you wrap inside a core, a core. Okay, you have a steel core here, and then you wrap around it, and this one will become solenoid. This is actually the basic construction of inductor, and the motor is actually a inductive load. So everything that use electrical motor is actually inductive load. So our home has a lot of motors. Inductive load. Yes. For the water heater, so water heater, it depends. Okay. It depends. It's sometime or they call also inductive load because we have the pump, water pump. You have the water pump. So that one is combination of R and also L. R is for the heating, right? R is for the resistor is because the heating, because the resistor absorb the energy and then it dissipate as a heat. So water heater is actually what we call R and L. And then actually the washing machine is also R and L because every single winding there is an internal resistance. So, but the inductor effect is much more major in the motor. Okay, so actually our load, our house is actually inductive load. Okay, so the power, the voltage and current, if you monitor the meter, is the meter of your home, the voltage and also current, you will see that your current will always lagging the voltage because our load is inductive load. Okay, our house is actually inductive. Okay. Oh, this one, example. I think we proceed this example with our next class. Okay. We have a lot of example here and also exercise. Okay, I think that's all for today. Thank you very much for your attention. And I will upload this in my YouTube channels and with the playlist, okay? Because in my YouTube channel, there are a lot of videos there. So I will create a playlist for this master course. And then you just refer to that. Okay, so thank you very much. And then I think you can try to solve this example 1 and example 2. Okay, then we will discuss and I will show you on the solutions in our next class. Okay, thank you very much. Assalamualaikum and have a very
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.